Hi, good evening everyone. Welcome to ACE Engineering Academy and ACE online platform. Today, most of you have written ISRO examination. So let us see first what is the weightage given in each and individual subject, and then we will discuss solutions for each and every topic that was asked in today's exam. So this is the total weightage given in ISRO electronics branch. From network theory you had 6 questions, signals and systems 9, analog circuits 8, digital circuits and VHDL. Digital circuits we had 8 and VHDL 1. Control systems is 10. So this is one subject where you had a very large number of questions. Electronic devices and VLSI clubbed together is 5. Electromagnetic theory 5. Communication systems we had 10 questions, actually 11 questions. One question we have taken it and kept in another part. Microwave we have 5. Electronic measurements and instrumentation 2. Power electronics is 4. Electrical machines is 4. Mathematics 3 and aptitude is 15. So on a whole the total questions were around 95. Sufficient time is there, and the most important thing in today's paper was comparatively easier, because when you compare with last few year papers, actually there were many questions where you have to think a lot and answer the question carefully. But today's paper we could see most of the questions are formula related. So if you can apply the formula correctly, within no time you had your answer. It is just less than 1 minute. You can easily score as many marks as possible. Okay, so I hope most of the students might have done very well in this examination. So let us go through each and every subject. What are the questions asked? So myself, Sarvan Kumar, I am communication faculty in ACE Engineering Academy. So first let me go through to the communication systems, and the other faculty related to their subjects, they will be continuing with the remaining part. So coming to the communication systems, so these are the questions that were asked in today's paper. Let us see one by one. This is a channel, it's very clearly given, it's a binary asymmetric channel, okay? Non-symmetric channel, probability of 0, 1 are given, and these are conditional probabilities, 0.7, 0.6, 0.3 and 0.4. So he is asking, what is the value of probability of error, average probability of error? So probability of error, directly you can write, here when you take 0, what is the probability of 0 becoming 1? So probability of 0 is given to as 0.2, probability of 0 that can become as 1 is 0.3, plus probability of 1 generation is 0.8, probability that 1 can become 0 is given as 0.4. So multiply them. So the total probability of error we can express as 0.06 plus 0.32. So you can express this value as 0.38. That's all. So this is how you can get your answer straight away. So he did not ask anything related with minimum probability of error. Then you can write this MAP or ML rule based algorithms and get your answer. Straightforward question. Right. Let's go through the next one. The bandwidth occupied by an 8 PSK modulated signal. So here modulation scheme is PSK and the value of M is 8. Where these IQC are the channels. When you take 8 as value of M, so obviously you will have 3 bit data that has to be transmitted. So that he is representing as IQ and C. N-tuple IQC toggle at a rate of 200 megabits per second. So RB is given 200 into 10 power 6 bits per second. So what is he asking? What is the bandwidth occupied? So what is the formula we can use for bandwidth? The default bandwidth is 2 into RB divided by log M to the base 2. So here when nothing is specified, we assume that data is transmitted using rectangular pulses. So I am just making use of the same thing. If it is Nyquist sampling pulses, then it would have been RB. Okay. So this bandwidth we can directly substitute these values, 2 into 200 into 10 power 6 divided by this log M to the base 2, log 8 to the base 2, you will get it as 3. So you are having 600 by 3. Okay, so 400 by 3, sorry, it's my mistake, just a moment. So this value, you will get it as 400 divided by 3. So around 133.33, 10 power 6, so you can express it as megahertz. That's all. So this would be your right choice. So once again, straightforward formula based question only, nothing very difficult in this. If you would have asked minimum bandwidth, then this value would have been divided by 2 because you will use Nyquist sampling pulses there. Next, given that C and DR, this is carrier to noise ratio of a 256 QAM, so again value of M is 256, operating at 12.5 megasymbols per second. So this is very important observation here. This is not a bit rate, he has given it as baud rate, symbols per second. So baud rate is 12.5 into 10 power 6. So when you want the bit rate, so this bit rate will be this baud rate whatever you are having multiplied by number of bits. Number of bits are nothing but that log 256 to the base 2, that's all. So this value would become 12.5 into 10 power 6 multiplied by 8. Okay, so that is a bit rate. And the next part that is given to you as 100 decibel hertz. So this is directly given in units. 100 decibel means it relates with your signal power. In hertz means he is giving that power bandwidth value. The value of EB by N0. So directly you can calculate the value of EB by N0. Average bit energy related with noise value. So that is the value that he is directly asking. So you just need to divide this 100 dB hertz. 100 dB means you will get 10 power 10, 100 dB. So it is 10 to the power of 10 divided by this value 12.5 into 10 power 6 into 8. So you will get directly this as 100 because 12.5 into 8 you will get 100, 10 power 8, so you will get 100. When you express it in dB, value becomes directly 20 dB. So your right choice is option. So pretty much formula based only. Units if you observe you will understand how to do. So directly you can take that decibel hertz and divide it with the bit rate. That will directly give you the value of EB to N0 ratio. Let's go through the next question. This is completely a theoretical bit, but question is framed a little bit differently. Noise phenomena arranged in an order of their dominance when plotted as a function of increasing frequency. So what is happening here? When you increase the frequency, which noise is dominant? That is what we can understand here. So you can straight away tell white noise is independent of frequency. So whatever the frequency you are operating with, white noise remains same. Transit noise is more powerful at high frequency. That means what? When frequency is increasing, the transit noise power spectral densities also will increase. That means the effect will be more. Similarly, the other type of noise which he has mentioned is flicker noise. Flicker noise actually is more dominant at low frequencies. So when the frequencies are low, then the noise is more for flicker. I mean the noise power is more for flicker. And when you have the frequency as very high, then automatically the next one that is going to come is this transit time noise. And it is independent for white noise. So whenever frequency is less, first one that we have to concentrate is transit. Okay, and whenever the noise is just a moment here, flicker and transit, right? And white noise is independent of frequency, and whenever the frequency is very, very high, automatically the transit time noise also will become very, very high. So based on that, we have to consider these conditions. So whichever the noise that becomes more powerful when frequency is more. So here axis he is saying as F. So x-axis you take it as F, and y-axis you can expect this as power spectral densities of different types of noise. So when it comes to white noise, it is independent of frequency. And when you take this flicker noise, its curve will be something like this. It is very high at low frequencies and decreases as the frequency increases. And transit time noise increases with the frequency. It is like this. So as frequency is very high, this noise power spectral densities will be high. So as the frequency, if you take, first is your the transit time noise, and then white noise, and then you will have the flicker noise. So I go with option D. That is how you can answer this. Okay. Little bit theoretical model. Next, when a carrier is AM modulated by 3 single tone signals of modulation indices, so directly mu1 is 0.5, mu2 is 0.5 and mu3 is 0.2. Then the effective modulation index, so what is mu t square? 1 square plus mu2 square plus mu3 square. So what will be this value? 0.25 plus 0.25 plus 0.04. So value of mu t square will become 0.54. So net modulation index will be root 0.54. That's all. Again formula based question. Simple one only, single tone signals with different modulation indices. Next, this is based on PCM system, baseband data transmission. So here total number of signals are 8, capital N, and the maximum frequency of the message signal is 2 kilohertz, and sampled at a Nyquist rate. So what is sampling frequency? Fs is 2 into F max. So this would become 4 kilohertz. Are converted into binary PCM signal using 256 quantization levels. So LR 256. So number of bits in your PCM system will be obviously 8 bits per sample. The data rate, what is the data rate? RB. Capital N into small n into Fs. There are no extra bits used. So directly we can use this formula. So this capital N is 8, small n is also 8, and Fs is 4K. So 64 into 4, 256 kbps. So that would be your right option. Okay. Let's go through the next one. What is the quantization noise power for an n-bit uniform quantizer with full scale voltage of 2B? So full scale voltage directly represents the difference of this Vmax and Vminimum. So that is given as a 2B. So this delta, our step size, it is Vmax minus Vminimum means 2B divided by 2 power n. So n bit quantizer, so it is n. So quantization noise power for a uniform quantizer is always del square by 12. That means this will become 4b square by 2 power 2 capital N into 12. So you will get a b square by 3 into 2 power 2n watts. That's all. So directly it will be option A. Formula based. Okay. Next, if a random communication signal has a PDF, so this is not actually capital PDF, you treat it as small PDF. It is giving you probability density function. Okay. For all values of x, then what is the relation between P and A? So what is the relation we have? The total area of a probability density function is always 1. So you are having 2A into, you split that limit. For negative values, your density function is like e power bx dx, plus for positive values, your density function is e power minus bx dx equal to 1. That's all. So you will have 2a into, both these integral values will be 1 by b equal to 1. So you will have 4a equal to b. So the value of b in terms of a is b equal to 4 into a. So option B would be correct. The minimum distance required for a linear block code to achieve a guaranteed correction for up to 5 errors is dash. So this is based on error detection and error correction. So here he is talking only about error correction. Based on Hamming distance, we can easily get it. So what is that D minimum? D minimum values should be greater than or equal to 2 into T1 plus 1. This is the logic we use when you are going for the number of bits that can be corrected, T1 error correction. So what would be the D minimum value as per the given data? Greater than or equal to 2 into 5 plus 1. So the value of D minimum should be greater than or equal to 11. So minimum D value that you need to get for correction of 5 bits for that given coding scheme should be 11. So your answer is C. Okay. Next, consider a random variable x with uniform distribution. So uniform distribution means probabilities in that given range will remain constant. So from -4 to 1 is your random variable x taking the form of uniform random variable. So your density function f of x will be automatically 1 by 5 because base is 5, height should be 1 by 5 to make the area 1. Now what is he asking? He is asking mean and variance. So mean you can tell directly. What is expectation of x? For a uniform random variable, mean value is midpoint. That means 1 minus 4, add these two and divide with 2. So it will be minus 1.5. So straight away you can eliminate these two. Either A or B will be the answer. Next he is asking variance. So what is variance? First find mean square value. Expectation of x square would become integral x square f of x is 1 by 5 dx. Limit is from -4 to +1. So it will be 1 by 5, 1 by 3. X cube means 1 minus of minus 64. You will get 4 cube. So it will become 65. So you can write this as 13 by 3. Okay. So what is the variance of this random variable? It will be this mean square value 13 by 3 minus this variance whole square means 2.25. Is it clear? Minus 1.5 whole square. So you will get this value like 25 by 12. So your option would be this A. Okay. Just simplify this, you will get that value. You will get some 4 point some value here. So 25, 4.2, the difference when you take it will be some 2 point some value. So the only possible choice will be that A. Okay. Right. So this is based on the concept of random variable. So these are the questions coming from the communication system point of view. All the questions I should say are straightforward only. There is nothing difficult in framing these questions. Within time you can do these things. So let us go for the next topic. My colleague will take the remaining part.